Sir, please begin.
Okay, fine. Rushikesh sir, please start.
Yes, yes. So good morning, everyone. I would like to introduce our guest. Uh, so we are delighted to welcome Dr. Kastro Kiran V, postdoctoral researcher at IIT Tirupati, as the research person for this webinar. Dr. Kiran specializes in advanced cementitious materials, including ultra high performance concrete (UHPC), internal curing concrete, and sustainable construction materials. With a strong research background in experimental characterization, durability analysis, and machine learning based performance prediction of concrete, he has contributed to several high impact journal publications and funded research projects. His work bridges traditional material sciences with modern AI and data driven approaches, making him uniquely positioned to provide insights into the future of intelligent concrete design and performance optimization. Uh, just a note to every candidate that if any participant has any query, they can ask their question in the chat box only. We will address them at the end of the session. Thank you.
Can I start the session?
Yes, Kastro sir, you can start your session.
Right. Thank you. Thank you once again. So I hope my screen is visible and my voice is also audible now.
Yes, sir.
All right. Right. Thank you. Right. Welcome you all. So in this webinar or in this presentation, I'll be focusing on the fundamentals to intelligence perspective on ultra high performance concrete, where this webinar will be driven mostly on four major elements. The first one is the materials required for UHPC. The second one is the mixed design aspect and the characterization, that is testing of the UHPC and testing standards, protocols, and all that part. And finally, we will conclude this particular session with the integration of ML, or how can we integrate machine learning in the mixed design of UHPC or also in the material characterization of UHPC. So in this presentation, I'll be broadly covering these 10 aspects, starting from why do we need UHPC to the basic understanding of the materials that are required in the UHPC, to the large scale production, and to the introduction of ML and utilization of ML so that we can use the UHPC concrete at a larger scale by using the advanced techniques, which is machine learning is one of the most advanced technologies that are currently running in the market. So this is the brief overview of what I'm going to present in this presentation. And coming to the first one, which is why do we need ultra high performance concrete? So what is the need for ultra high performance concrete? What led to the discovery or the need for ultra high performance concrete? So if you have noticed the concrete hierarchy, so the concrete hierarchy can be broadly categorized into four ways. One is the normal strength concrete. The second one is high strength concrete. The third one is ultra high performance concrete. And the last one is reactive powder concrete. This is how I categorize the concrete based on the strength perspective, alongside the durability and the other mechanical properties as well. So in general, any normal strength concrete refers that if the strength is between 20 to 50 megapascals, that can be typically considered as a normal strength concrete, which has the water cement ratio ranges between 0.45 to 0.65. And usually this normal strength concrete has a higher amount of pores. That is why that led to most of the deterioration characteristics or most of the vulnerability prone areas. And to overcome that, we have got higher strength concrete, where we'll be attaining its strength up to 100 megapascals by minimizing the void content and also by minimizing the water binder ratio as well. And to overcome the limitations of high strength concrete, especially in high rise structures or thin walled sections, we got an advanced one, which is ultra high performance concrete, where the strength will vary widely between 120, 130 megapascals to up to 200 megapascals, where we can drastically reduce the water binder ratio. And at the same time, the minimization of pores is also possible because of the material composition that is available in the UHPC. And again, we got a much advanced and much higher grade of concrete, which is reactive powder concrete, where we can typically see the strengths greater than or equals to 200 to 220, 230, and even sometimes going up to 600 megapascals. There are some literature which has reported even 600 megapascals of strength, particularly the compressive strength in the reactive powder concrete. And all it's because of the material composition, the water binder ratio, and the reduction of porosity in the reactive powder concrete. So this is typically the concrete hierarchy. And as we proceed with each concrete type based on its strength, obviously we can increase the service life of the structure as well. As you can see, so for normal strength concrete, the service life can be expected up to 50 years, as 50 to 60 years roughly. And when we go for high strength concrete and ultra high performance and reactive powder concrete, the service life of the structure can be increased at a larger scale, which is an economical, at the same time, which is a good sign of as a concrete technologies or as a concrete researchers. But we got some limitations with conventional curing concrete or conventional concrete. Typically, the conventional concrete lacks in the zone of tensile strength, which gives a very less amount of tensile strength, approximately 2 to 5 megapascals. That's the maximum that we can attain in the low tensile strength of conventional concrete. And also that comes with pure durability aspect because of larger amount of pores compared to other types of concretes. So this also is susceptible to higher amount of durability conditions, such as, let's say, when I expose a conventional concrete to the acids or to the sulfates, there is a high chance of deterioration might happen within the first 14 to 28 days or within first 56 days itself. So that's again one of the problems with conventional concrete, and that leads, the durability problems leads higher maintenance cost perspective. So that is also again one of the disadvantages. And coming to the carbon footprint, especially the life cycle assessment or the life cycle impact, these things, they are also, like conventional concrete is also prone to consume too much amount of materials, and that leads to higher amount of carbon dioxide or the carbon footprints, release of carbon footprints will get increased. That's again one of the disadvantages. And with conventional curing, conventional concrete, we can attain the section thickness, which is of a larger scale. But in real time, when we go for large scale construction, especially the girders or the bridge decks, in all these cases, we need slender sections or very thin elements, providing the equal amount of strength or the better strength with better durability and better strength perspective as well. So considering all these limitations of conventional concrete, we got a better one, which is ultra high performance concrete. So in simple terms, we can define ultra high performance concrete is something which will give the strength in between 150 to 250 megapascals. Again, this is not a standard value. That's a typical value which is reported across the literature which I have studied. And this particular ultra high performance concrete will yield up to 15 to 30 megapascals of flexural strength, which is again a very good sign of utilizing the ultra high performance concrete in the bridge decks or in the girders or in the large scale construction. And we can also minimize the crack width, which will be less than 0.2 mm, which is again a better one compared to any other types of concrete that is available at the moment in the industry. And that also has less amount of permeability as well because of its dense packing and because of the material composition, which is very fine amount of materials will be used in the preparation of ultra high performance concrete. That leads to lower amount of permeability. And again, in order to attain this flexural strength or tensile capacity to the ultra high performance concrete, it is essential to use the steel fibers. So that's how the ultra high performance concrete is prepared. And typical percentage or even up to 5% also we can extend. But anything that goes beyond 2% will lead to the workability issues and also will lead to negative effects on the compressive strength as well as the other properties as well. So this is in simple terms what is ultra high performance concrete. Now the question comes here is, why do we need UHPC? So the first thing is infrastructure demands. Let's say when I'm constructing lengthy structures or tall structures or the structures which are more susceptible to corrosion or more susceptible to any kind of vulnerabilities related to durability. So because of this infrastructural demand, again, we need to go with ultra high performance concrete. And when we need a slender sections, let's say I need a thinner elements in terms of structural perspective, not just in terms of material perspective, then again, we need an alternative material, which is UHPC again. And UHPC also provides better durability conditions, provided if right amount of materials, right combination of materials are used, we can attain exceptional durability characteristics, which can lead up to 100 plus years of lifetime of the structure. And when combined UHPC with certain kind of seismic performance, that can also increase the seismic performance of the structures as well, which is nowadays being preferred in the construction of bridges or bridge decks, especially focusing on seismic performance alongside the priority given to the sustainability aspect as well. So where we can use less amount of materials, which will produce greater amount of strength or greater amount of durability conditions in the real-time scenarios. So that's the need for UHPC. And coming to the real-world applications of UHPC, so mostly the UHPC is preferred to work with bridge decks, bridge joints, or even the protective structures, the architectural facades, marine structures. Particularly, this is where we are actually I'm working with the bridge decks, joints, and the marine structures. And for retrofitting also, it will be very easy in the long run as well. And this is particularly preferred in the seismic zones where we can expect an earthquakes of magnitude anything greater than or equals to 4.5 to 5. So there are proven conditions or proven case studies which said that when we use UHPC for the construction of large-scale constructions, especially the bridge decks or marine structures, that has resisted the seismic performance, which is again a good sign for the concrete technologies as well. And coming to the UHPC design standards on materials, there are across the globe, there are multiple design standards are available, and these are some of the popular design standards for UHPC, where you can refer to when you are working on UHPC mixed design or UHPC testing. So there are different protocols. So you can use any one of these protocols or a combination of these protocols to make sure how the things are going to work when you are testing in the laboratory conditions, or even when you take it to the large scale field testing as well. And we preferably work with either FIB model code, which is a standard one. Again, that comes with fiber reinforced. It's not just the UHPC thing. It is ultra high performance fiber reinforced concrete provisions. So especially in UHPC, we'll be using fibers, especially the steel fibers we'll be using. So in that case, FIB model code and ASTM code is preferred. But however, in the recent advancements of IS 456-2000 and also IS 1026-2025, so we are getting certain kind of advanced mixed design for UHPC as well, and that is still being under consideration, and that has recently got published as well. But the final outcome has to come at, so where we can utilize it at the laboratory conditions to test at a smaller scale level to check the functionality of UHPC mixed design and all these parts. So these are the different global standards that are available in order to do the mixed design and also the performance testing of UHPC. And coming to the materials of UHPC, so UHPC doesn't consist of any kind of coarse aggregate, which is one of the most important thing that we need to keep in mind. So because of the materials that we are using in the UHPC, particularly the finer materials, that is how it leads to higher strength and higher durability and dense packing of the materials. And alongside that, it is also important to focus on the durability conditions as well, which most of the researchers will miss out considering only strength as a primary perspective. Yes, strength is also a good one, but alongside that, it is also important to check the structural performance and the durability performance as well. And practically also, we need to check whether life cycle assessment or life cycle impact, carbon footprint also being considered in the design aspect as well. So the materials include the cement, which is typically the ordinary Portland cement. So we cannot go with the PPC, which is Portland pozzolanic cement, which is, again, we know that PPC has certain amount of fly ash, which will be combined with. And when you have something called fly ash in your cement or in your concrete mix, that doesn't lead to early strength, which will lead to the later day strength, that is at the end of 58 days or 56 days. That's how we typically get it. And the silica fume percentage will be typically used between 15 to 25% by weight of the cement. Again, we can reduce this silica fume content also. So in the present work, which I'm currently working, so we are not even using the silica fume, but still we are able to attain 130, 140 megapascals of strength. But again, however, we are using microfine silica as an alternative for silica fume, but that is also at a very minimal level. Still, we are able to attain 120, 130, and even 140 also. We recently touched that particular amount of strength. And in our mixes, we are not even using the quartz powder as well, which is a very fine material. But in typical UHPC mixes, we'll use quartz powder. Again, quartz powder is also a costliest material. It's not a cheaper material. So, but considering that as a primary perspective, quartz powder can also be eliminated, even though despite eliminating the usage of quartz powder or even quartz sand, we can still attain 150, 160 megapascals of strength as well, where there are some studies which proved that without utilizing quartz powder and quartz sand, we can still attain the required amount of target strength as well. And in the UHPC, the steel fibers is one of the most important element or most important combination of materials. Particularly, we use different types of steel fibers, such as straight steel fiber, hooked and steel fiber, and other types of steel fibers are also used, which I'll explain in a while. And typically, the steel fiber will be having with a volumetric percentage of 1 to 3%. That's a typical percentage that we can use. Again, this 3% is the higher bar. So we can limit that to 1.5 or even 2% also, which will yield better strength as well. And superplasticizers is one of the most useful material in the determination of or in the preparation of UHPC, because flow is considered as one of the primary aspect. Particularly in the recent researches which are happening, self-compacting UHPC is gaining more prominence. So for that self-compacting condition, we need to use superplasticizers. Particularly the PCE-based superplasticizers are primarily preferred than the SNF or lignosulfates or any other families of superplasticizers. And the critical superplasticizer dosage will range between 0.1415 to 0.2 to 0.25. That's a typical dosage which will give a better flow. At least you can get 220 to 30 mm of spread diameter, which you will be testing on a flow table apparatus. And alongside all these materials, we can also use supplementary cementitious materials such as silica fume, fly ash, metakaolin, nanosilica, considering the aspect of sustainability and also the performance. So these are the typical constituent of materials that have been collected from various literature. So this can be helpful for the researchers or the PhD scholars who are currently working in the UHPC area. And coming to the supplementary cementitious materials such as silica fume, nanosilica, metakaolin, rice husk ash, and all these things. So these are the typical dosages that we generally prefer or that we have observed over a period of 6-7 months of deep understanding of the existing literature on UHPC. This is what I have consistently noticed in the existing literature with respect to how much amount of SCMs, that is supplementary cementitious materials, can be utilized in the preparation of UHPC so that we are getting the better strength and better pozzolanic activity, considering the SiO2 content and the particle size, especially the D50 size in terms of micrometer. So that is in terms of supplementary cementitious materials. And coming to the aspect of steel fibers, so we have different steel fibers that are currently available in the market, particularly the straight fibers, which are also in terms, we call it as smooth fibers, hooked end fibers, twisted and helical fibers, and PVA and PV fibers, that is particularly the polyvinyl or polyethylene glazed synthetic fibers. And among all of these fibers, it is proven that either straight fibers or hooked end fibers are yielding better strength. Again, combining the hybrid fiber combinations also gives much better tensile capacity or much better structural perspective as well. But in the real-time scenarios, we mostly try not to use the helical type of steel fibers or PVA or PV type of steel fibers, primarily because of its the cost aspect, and also the production also is very less compared to the straight fibers and the hooked end fibers. So the most common type of fibers which we generally get in the market is the hooked end fibers. But there are some suppliers which will provide the straight fibers also, which again gives, when we use a combination of fibers, that again leads a better strength as well. And particularly when we use a combination of steel fibers, it is very important to focus on the volumetric percentage of each type of steel fiber. So when we use the combinations, obviously the focal point has to be on the combination. Let's say if I use 1% of steel fiber and 1.5% of glass fiber, so how the material will behave. So what properties will get enhanced, what properties will get decreased. All these things has to be focused at a large scale when we are using hybrid fiber combinations as well. Alongside that, it is also important to focus on the workability, especially the flow characteristics of UHPC, which is a primary thing in the real-time scenarios. So that also need to be considered. So when we change the volume of the fibers from 0% to anything greater than or equals to 3%, some properties will get increased, which is very much valuable. And there are some properties which will get, which will show a negative effect. That's again not a good sign to produce a durable and high performance UHPC concrete. So that's again one more thing that we need to consider as we are working on UHPC pattern. And packing density is one of the most important things in the mixed design of UHPC. Without doing a proper packing density analysis or packing density test, it is impossible to attain maximum packing. And if you are not able to achieve the maximum packing, obviously that leads to reduction of strength and a higher amount of pores, which will also cause the durability issues as well. And there are different packing density models that are available or that are reported in the existing literature. So these are some of the models, and the very popular model which we have is Anderson model, which is the very most widely used model across the mixed design of UHPC. So you can adopt this particular model to attain or to ensure the packing density analysis, or to see how much packing density is being attained when we use combination of all the materials that we have used. So most of the people, how we check out with this packing density is we'll check the packing density with only the cement, silica fume, and any other materials that are used as supplementary cementitious combination. But in general, whenever we are testing the packing density of UHPC, it has to be given the utmost preference to all the materials, whatever that we are using in the preparation of UHPC. So for all the materials combinedly together, it is important to measure the packing density analysis. We have microstructural studies which can be done using the packing density, and then we can write the Python code or the MATLAB code if you are good at it. So you can run an analysis so that we can get to know how our packing density will be coming with respect to the Anderson models or any of the models that are available. So whenever you are comparing your packing density analysis with any of the existing models or the most famous model, which is Anderson model, so make sure the curves are plotting in a similar line. So that's, or at least close to the existing model curves, your curve should also come. So that actually tells your packing density is almost as close as to the existing models. Until or unless your curves are not close to the existing models, so what it yields is it might yield a better strength, but it might not yield the better packing density. So, and when we don't get better packing density, in the long run, the structure will get affected, and also the durability can be one of the most concerning factors also. And why packing density is critical in UHPC? So again, as I was mentioning, in UHPC, there is no fine aggregate, there is no coarse aggregate. So it is all the combination of the finer particles so that we can get the maximum packing density. So when we get maximum packing density, that actually yields the strength, the durability, and also it shows an effect on workability as well. So when we have better packing, obviously we'll have lower pores or lower pore percentage, and that actually leads to strength. But again, durability can also be considered as a key role in the design of UHPC, because just because we are getting higher strength to the concrete, let's say 150, 200 megapascals of concrete, we cannot exactly tell that that might yield better durability conditions. Let's say the permeability or the porosity or the softivity conditions or the chloride permeability or acid resistance, any of these carbonation tests, any of these things also has to be tested, because when we construct structures with respect to UHPC materials, we expect the structure to be there for at least 150 plus years of age. So when we are constructing a structure which will stand still with 150 plus years of age, it is utmost preference to be given for durability as well, alongside the strength also. So that's something why packing density is critical in the design of UHPC thing. And the typical mixed design methodology that we generally follow in the preparation of UHPC is we are going to define the targets first. That's the primary thing that we are going to focus on. So once we define the targets, then we are going to select the materials. So what are all the materials that we need? And then based on the materials, whatever that we have used, we need to do the particle size density or particle packing density, which is PSD analysis or PPD analysis, particularly by using the microstructural studies, that is by using the XRF or XRD analysis of all the material combinations that we are using. Once we get this particle packing density analysis, then only it is recommended to do the mixed design, and then finalize the mixed design with appropriate water binder content, superclass size and dosage. And particularly when we are finalizing the superclass size and dosage, it is essential to attain a minimum mini slump flow of anything greater than or equals to 200 mm. But if you are getting a flow of 220, 230 mm, which is very good, but don't go beyond 250 mm, because that leads to segregation or that leads to bleeding of the materials as well. So keep the flow less than or equals to 230, or that would be more than sufficient. But don't go anything less than 200 mm. That's again a bad sign of flowable nature to the UHPC, where you cannot attain easy flow, especially if you are focusing on self-compacting UHPC based things. And it is imperative to do the multiple trial mixes, because it's not that in one trial we are going to get the entire properties or the desired characteristics of UHPC. It's an iteration of multiple materials, as we know that any concrete that we are preparing, so it is imperative to do the multiple combination of trial and error, so that only we can finalize the final mix design, followed by we can take it to the large scale testing or field level testing as well. So that's with respect to the mix design methodology. And coming to the mechanical properties and the test methods, particularly we'll focus on the compressive strength, which is again tested on 100 mm cubes. That's a standard one that we are going to focus on. So anything with 100 mm cubes, that is more than sufficient. But if you are going with 150 mm cubes also, that is fine. But typically when we go with UHPC in the laboratory testing, we'll go with 100 mm cubes. That's more than sufficient with 100 by 200 mm cylinders also. That's as per following this guidelines of IS code as well as ASTM standards also. And there are different mechanical properties that we need to focus on. Particularly, we'll generally focus on compressive strength, tensile strength, and flexural strength, which is good at a primary level. But when we want to know at a large scale level, it is very much essential to find out the elastic modulus and the fracture energy and creep and shrinkage, which are basically the structural point of view. These are the primary tests that you need to consider. And again, all these are the basic tests that you need to do. So the first three, that is compressive, tensile, and flexural strength, these are the very basic strengths where you can find out the minimal properties or make it minimal mechanical properties. But when you go with structural perspective, these are the very basic minimal structural perspectives or structural characteristics. But alongside these 6 mechanical properties, there are also n number of properties that are available. Let's say the cyclic loading or any kind of fracture energy tests and all these things that can be customized as per the research direction that you are working on, that you are going to work on. And coming to the standards of testing, so we have different standards across the globe. So mostly you can prefer either ASTM standards, which is a standard one, or you can also go with Indian standard codes as well, which will give almost equal range of testing standards. But again, here when we are testing with any standard protocols, let's say if you are following ASTM standards, make sure you are testing with the average loading rate, whatever that is specified in the code conditions. Because if you are testing at a loading rate of whatever that is essential or whatever that you have the availability with, that may not yield the better strength or that may not yield better properties also. So make sure loading rate is also considered as the primary aspect when you are doing any kind of mechanical property testing. And coming to the durability studies, which is often missed out in most of the studies, or which is often overlooked at most of the studies, particularly in the UHPC concrete. So chloride penetration, carbonation resistance, freeze thaw, alkali silica reaction, alkali aggregate reaction. Again, here, despite we don't have alkali aggregate reaction, we have fine aggregate, we have quartz sand, quartz powder and all these things. But still it is essential to find out even alkali silica reaction and alkali aggregate reaction. Despite that, it is also imperative to focus on the fire and thermal resistance, which is again very limited literature is available related to fire and thermal resistance. If you are focusing on fire and thermal resistance, that gives a broader perspective, especially if you are testing UHPC at elevated temperatures, let's say 200, 400, 600, even up to 1000, 1500 degrees of centigrade. So that gives better perspective towards understanding of UHPC under exposure of elevated temperatures. And there are different curing regimes that can be followed in the UHPC. So the standard water curing, that is generally something that can be followed. But when we use steam curing, that's something where we are attaining better strength. So in the current research, which I'm currently working on, we are also focusing on steam curing, where we are looking at the strength can drastically increase by up to 30 to 40 megapascals of strength. But again, that may not be feasible in the real-time scenarios, particularly with steam curing. But when you are going with precast structural elements, especially when you are going with bridge decks or the girders, these are all precast elements. So when we go with precast elements, obviously we have in the laboratory conditions or in the factory conditions or industrial conditions, we have the possibility to go with steam curing. So if possible, try to do steam curing also, so that you will get to know how the things are getting validated between the different types of curings that we have compared to steam curing that we have. And coming to the machine learning models, which is again one of the most useful thing to avoid the large scale testing. But again, when we do machine learning, so people often confuse with, okay, do we need to generate this much amount of data to perform machine learning? It is quite obvious that when we do any machine learning analysis or when we do any AI-based analysis, we need a large amount of data set. It's not that generally for people who are from civil engineering background or people who are into research-based civil engineering background. So we know that it is not so possible to generate large set of data, which is a proven fact, because when we do any kind of testing in the laboratory conditions, we'll mostly do, suppose for example, when we do the compressive testing, compressive strength test, or when we do any other mechanical properties, we generally do it at 7 days, 14 days, and 28 days. That's the typical pattern that we follow, or the typical timeline that we generally follow. So when we test at each aging period, let's say at 7 days, we mostly test 6 specimens, and we'll take the average of those 6 specimens, we'll find out the standard deviation, and we'll report what is the average strength combined with standard deviation. So now keeping that into consideration of very minimal amount of data set, so it is not so possible to work with machine learning models or to implement machine learning models, particularly when we have limited data set. So people who are working in the UHPC or any kind of concrete, it doesn't necessarily need to be UHPC. So I'm generalizing this particular thing with any types of concrete combined with machine learning. So when we want to go with machine learning, try to generate the data, especially at the laboratory conditions, because only when you try to generate the data, we'll not get the problems of overfitting or underfitting. So we have two major issues when we do machine learning analysis. We have overfitting and we have underfitting. So that's again a problem when we do the machine learning analysis or when we run machine learning algorithms. So keeping that into consideration, try to generate as much as data possible, or at least you get the databases. There are different databases available in the open source models in the browsers. So you can go to any browsers and you can find the large data set or open source data set that is available. You can also do the preliminary testing on the open source data set so that you will get to know how your model is performing or how your model is behaving. And then you generate the data as per your mix design or as per your mixes. And you can compare so how the models are behaving with the existing literature to the laboratory tested literature. So that's something which I would like to tell before proceeding to machine learning analysis. And here, as we generally know, just a basic introduction towards machine learning is, it is something where you are training a machine or you are training a model to explicitly learn on its own. So that the code or the machine will understand the patterns, various patterns in the mix designs or various patterns in the materials, the properties and all these things. And by using the combination of all these materials, machines will understand what is the pattern that it is getting followed, and then it will give the desired outputs. And again, how does a machine understand the pattern? It's not that just because you have the data, machine will understand our pattern. It's not in that way. So obviously, we need to focus on writing the code, which is again a Python code. That's something which is preferred in the real time. So artificial intelligence is a broader area, but when you come to machine learning, which is a subset of artificial intelligence, and when we come to deep learning, that's again a subset of machine learning. So deep learning is a very narrower approach of doing the analysis, but whereas machine learning is something which is a kind of light, larger scale approach compared to artificial intelligence. So artificial intelligence is a very wide range of broad field, but if you want to narrow it down to a little extent, you can go with machine learning. But if you want to do any deep learning analysis, let's say if you want to perform the deep learning analysis, obviously it's very much essential to generate at least some 10,000, 15,000 of data, which is again not so possible in the real-time scenarios, particularly for people working in the research areas of UHPC or any types of concrete. So keeping that into consideration factor, it is important to decide what type of thing that you want to incorporate in your mix design or in your testing. So is it AI or is it ML or is it DL? So it depends on the data set that you have the chance with or that you have the availability for. So when you use ML models for engineering models, basically how it works is ML models will recognize the pattern. So how the things are getting changed. Let's say when I change a combination of material, how the properties are coming, how the durability conditions are getting assessed. So that pattern recognition is possible with machine learning studies, and we can also perform the nonlinear modeling. Suppose, let's say when I keep all the materials as constant and when I change only one particular material, how does it behave? That's again one thing that we need to focus on. And the generalization is possible, and the speed of testing, that's something which is most feasible. Instead of testing months and months of testing in the laboratory conditions, we can generate a data and we can get the code once we train the model by properly splitting into the data model and the testing model, that is training model and the testing model. So we can actually attain the data, or we can actually attain the results at a very minimal time itself. Let's say hardly 1 or 2 days if you work practically, that will yield better properties or better faster results. That's again keeping into consideration of the data set, which is a primary factor. And coming to the workflow of machine learning. So whenever we use any machine learning models, we'll first define the problem statement. So what are we trying to find out, or what are we trying to determine using machine learning models? So that we need to define as a problem statement. And then the data collection, you can do the experimentations in the laboratory conditions, or you can collect the literature data, or you can also collect the open source databases that are out there in the market. And then we need to do the processing, which is basically the pre-processing of the data. That is, if any missing data is available or any missing labels are available, if you want to label the data, you can label the data, encoding, normalization, all of these things can be done in the pre-processing. Followed by, we'll do the feature engineering, which is extraction of the limited amount of data or extraction of selected amount of data, particularly with respect to dimensionality or dimensional stability of the data. And then we'll select the models, what models we want to use, and each model has its own condition again. So what are you trying to solve? That depends on what model that you are selecting. So let's say if you are trying to solve on compressive strength, and if you are selecting a model which doesn't yield to produce the compressive strength results, there is no point in doing machine learning analysis. So this is where actually most of us will miss out also, because the lack of knowledge on machine learning, which is a growing technology, particularly in the civil engineering domain. So it is important to understand the fundamentals of machine learning. So which model, what are the models that are there, how these models will work, what is the thing that happens in the background. So all of these things we need to understand before we directly jump into any of those things, okay, performing the machine learning algorithms. And then we'll train the data, we'll have to tune the data, and then we'll do the evaluation metrics. Particularly, we have 4 types of evaluation metrics, that is coefficient of variation, RMSE, MAE, and MAPE. So once we do these evaluation metrics, then we'll have to finalize which model is yielding better evaluation metrics. And then finally, we can do the sharp analysis also, which is extendable analysis. That's again a very good research perspective as well. And these are the key ML terminologies that we have. So I believe you have an idea about on all these things. So I don't go into the details of these things. But anyway, you can look into these ones in the later case also. And there are different categories of machine learning models. As I was telling some time back, we have supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. These are the broad categories of machine learning. And again, here semi-supervised learning is something which is not so popularly used, but it is used popularly for UHPC based experiments. So that's why this particular semi-supervised learning or semi-supervised modeling is something which gives better results, and also at a very much fast. But again, supervised learning, unsupervised or reinforcement learning models also can be obtained. And again, in each category of machine learning models, we have different models that are available, such as regression model, classification models, such as neural networks, SVR, random forest, XGBoost. Like this, we have different models that are available. So whenever we are doing any machine learning analysis, it is very important to find out which model you are looking for, what is your objective with your machine learning analysis. So the objective has to be clear. Once your objective is clear, you need to know which model will fit for the data set what you have, and which model will give you better results with the analysis that you want to perform. So these are the different categories of ML models. And coming to the scope of ML, particularly in the UHPC research, where we have different scopes that are available. So why machine learning for concrete, or particularly the UHPC research? So generally, as I said some time back, whenever we do the testing in the laboratory condition, we'll do it at very minimal days. Let's say our minimal sample set, minimal curing days, we are going to do the test. So that actually will not give large amount of data set. And when we do this kind of testing, so there comes some problems, such as experimental costing. Suppose, let's say if you want to cast one batch of the mix, one complete batch of the mix, that might yield to 15,000 to 50,000 rupees. Again, that depends on what type of materials, combination of materials, and all those things. And also, we need to wait for 28 days to evaluate the strength parameters, the maximum 99% of strength can be obtained only at the end of 28 days. So that comes with some problems. So you need to wait for 28 days. You need to spend too much of amount. You need to invest too much of time, too much of labor and all these things. And that is again where ML comes into play. And you cannot easily determine how the interactions are there between the different materials. Let's say I want to find out the interaction between cement, silica fume, superplasticizer, the combination of fibers. When I change a particular percentage of material, how the interaction will be there, how the behavior will be there. This nonlinear interaction is something which is not possible to determine with the experimental studies. We can go it up to a level, but when we want to do it at a deeper level analysis, we need to know at a large scale. So that is again a limitation with normal laboratory scale testing. And the data mining is also a very important thing because there are hundreds of databases that are available for any kind of concrete, particularly the UHPC. I could see there are almost 10 to 15 databases are available. So where it will yield huge amount of data set, almost 1 lakh, 1.5 lakh of data is available in the global outreach. So you can use those data and you can work with that. So these are the main conditions why machine learning can be used in the concrete and also in the UHPC research. And the scope of machine learning will be particularly focused on the mixed design aspect. So where very few researchers has focused on machine learning combined with mixed design. Let's say if I give a target strength, this is the target strength that I want to use, that I want to get, and these are the materials that I want to use. There are very limited models which are giving the complete material properties or material characterization or the combination of materials. So maybe you can work on that area, which is also something that I'm currently working on by collecting the data and all that part. And compressive strength or mechanical properties prediction is quite common in any ML-based approach, not just in UHPC. If you take any concrete, 90 to 95% of the studies will mostly focus on the prediction of strength parameters. It can be compressive strength, spread tensile, or flexural strength. That is also fine. But most focus is there. So coming to the other standards such as life cycle analysis or cost analysis, you can also incorporate machine learning to perform the life cycle analysis or even the cost analysis also. So we have different softwares that are available to perform the LCA or any kind of life cycle assessment test. But alongside those software analysis, we can also incorporate machine learning to perform life cycle analysis where we can get the environmental carbon footprints or embedded energy or the total cost of the ownership, production cost, the release of carbon dioxide emissions. All these things can also be utilized with respect to machine learning as well. And coming to the fiber orientation prediction. So fiber orientation is also one of the things which will decide the strength of the concrete or strength of UHPC. So that can also be performed by using ML, particularly when we have the microstructural images of your entire sample, not just a portion of the sample. I'm talking about entire sample. So when I say microstructural images of entire sample, we have to go with 3D sampling or 3D imaging techniques, which is ultra scanning. So again, that comes with very costly experimental technique. Ultra scanning is a very costly experimental technique. But if you are able to achieve the ultra scanning for large set of samples, it will be very easy to find out the fiber orientation prediction with respect to machine learning models. So based on whether you are compacting, whether you are vibrating, whether you are hand compacting, whether you are doing both hand compaction and vibration, or whether you are doing self-compacting. So based on all these conditions, you can assess how the fiber orientation will influence the properties of any concrete, particularly the UHPC concrete. And the microstructural characterization, this is what I was telling, CT scan, which is a micro level scan. This is again very costly things. This microstructural analysis are technically very costly things. But if you are able to produce the data, there is a very high chance that you can contribute to the outside world where people can depend on your experimental analysis, particularly with respect to microstructural analysis. And this is where the current research is lacking also, especially in terms of UHPC research. Again, in the normal concrete also, this is where it is lacking. So most of the researchers has particularly focused on strength prediction or the mechanical properties behavior prediction. There are very few studies which focused on mixed design, life cycle, and the microstructural characterization with the implementation of UHPC. So that's where you can also look after and look into it as well. And these are the different literature surveys that we have used in our current ongoing studies for different ML models prediction or different ML models adoption also. So this is just for an overview. with the selective studies and limited predictions or limited data that is available. And coming to the key research areas, particularly in ML UHPC, so compressive strength prediction, which is most commonly studied, as I was telling some time back, it is a most commonly studied area, which you don't need to focus on a large scale, or you don't need to focus it as a key machine learning approach. You can focus it as one of the machine learning approach, but don't focus this as a key perspective, particularly when you are writing research papers or when you are doing any presentations in the international conference or in the national conferences that are happening. So focus more on this tensile and flexural strength, which is very much needed for HPC design. And workability prediction, this is also something which very few researchers has done it. I could see very minimal amount of research that happened with workability prediction of UHPC, particularly with respect to ML based thing. And creep and shrinkage, obviously, that has a very large scale scope in the real time scenarios. So that can be considered as one of the key research areas in your designs. It can be any design, like it need not be UHPC, but I'm just focusing on UHPC. So whatever things that I'm giving it here with respect to ML thing, so you can incorporate this with any of your concrete mixes or any of the concrete types that you are currently working on or that you are planning to work on. So these are the key research areas in the concrete, generalized to concrete and narrowed down to UHPC. And how can we generate the data? This is one of the common questions that we generally get, because when we go with ML, we have large amount of data. So it is very much important to find how to generate the data and how to collect the data. So when you want to collect the data, obviously we need to do multiple amount of literature sets or collect the literature data set. So from the collection of the literature data set, we can do the prediction of the compressive strength either at 28 days or even at early days, let's say 7 days, 28 days, 14 days, or in the later days, such as 56 days also, particularly if you are using fly ash as one of the supplementary cementitious materials. So this is one scope with respect to compressive strength prediction. The second scope is the durability prediction, where you can find out RCPT test, that is rapid chloride permeability test. But again, RCPT has its own limitations, so it's better to go with rapid chloride migration test, which gives better thing. So instead of measuring just the current that is passing, you can also measure how much amount of chloride is migrating or chloride is passing through the sample from one end of the sample to other end of the sample. That can also be considered as one of the scopes. And there are different methods that are available to collect the data, particularly with respect to ML studies. First thing is you can perform the laboratory tests and you can collect the data. That's a very basic thing. Or if you have the lack of data, you can collect the data from the existing literature or existing databases. That's also something which you can compare with your existing data. And data augmentation, this is also augmentation models, which has very limited, when you have limited data set, this can be used. But again, coming to the publication scope, this has very limited publication scope, if I have to talk in terms of publication perspective. But anything that you do with these three things, that is laboratory testing or literature data set or using the open source databases, that has a wide range of scope in terms of publication perspective as well. And so the data processing involves 5 major steps. One is the data cleaning, such as removing the duplicate values, removing the unwanted data. That's basically the data cleaning. And then feature encoding, so where we are going to categorize the different variables that are there in our mixes. Some mixes might use steel fiber, some mixes might use glass fiber, some mixes might use some other types of fibers. So that is basically called as feature encoding, where you are going to categorize the different variables that are available for different mixes. And then you have to normalize the data or standardize the data, particularly with respect to what is the minimum range, what is the maximum range, what is the scaling. And then you can use the neural network model or support vector regression models, SVR models, or tree-based models such as random forest, XGBoost models. And then you can perform the analysis. And finally, you can do the feature selection by using certain type of correlation matrices. And then you can do the train and test splitting. Generally, we use 70-80% of trained data and 20 to 30% of data as a testing data. So in the research which I mostly focus on, particularly with respect to ML, I'll keep maximum data for training and minimal data for testing. So I'll keep 70 to 80% of data as a training data and 20 to 30% of data as a testing data, which is again standard approach that we generally follow. And then it is very much essential to know the k-fold validation. So when you have more amount of more layers of testing. That's typically called as hyperparameter tuning. So if you do more folds, let's say if I do 5 folds, 10 folds, 15 folds, that will become a repetitive process. When you do the repetition of data, it will collect randomly selected data and then it will perform hyperparameter tuning. That actually gives better results instead of overfitting or underfitting. So we'll get a feature extraction or probable density curves also. And the different ML models, particularly for UHPC available are regression models, the neural networks, support vector regressions, random forest, and there are other types of models, particularly if you are focusing on deep learning. So convolutional neural networks, CNN, and LSTM models are also something which are preferred. But again, when you want to go with deep learning, as I was telling earlier, so deep learning is a very narrow set of machine learning or even with AI. So when you want to go with deep learning analysis, obviously you need to have large amount of data set. So for that reason, only if you have the large amount of data set, prefer to go with deep learning. Otherwise, stick to the fundamentals, that is machine learning models. So the different categories of ML models, that is more than sufficient. And the neural networks is also one of the most popular ML things that has been reported in the literature. But again, neural networks has become nowadays very fundamental testing. So when you possess any neural network modeling in your research papers or in your thesis, the neural networks has been given the very least amount of priority because that's a very basic thing. So whenever you want to do any ML analysis, neural networks is being considered as a very fundamental test that you need to do. The larger scale testing will come only when you do large scale testing. That's something which we need to look after. So that's also something which I want you to focus on. And there are different tree-based models such as random forest, XGBoost modeling. Like this, we have different models. So you can look into which are the typical models that can be used. Again, these are all generalized models. So you need to focus on what is your core area. And according to the core area, you need to focus on the selection of the models also. And there are support vector regression models and GPR models, that is Gaussian process regression models. Again, these models will also yield different types of parameters, different outputs, different values, different strength parameters, and all these things. So particularly when you want to go with UHPC, so I would try to prefer to go with SVR and GPR models rather than the basic neural network models. Again, fundamentally, these models are going to work on neural networks only, but don't keep neural networks as a primary testing objective. Okay, go at a deeper level. And how to choose the right model. This comes a major issue for beginners, especially in the machine learning domain. So when we are doing machine learning analysis, we'll do multiple models and we'll just compare models. That's good. But why are you doing more models, or why are you selecting huge amount of models? It's not required technically. So when you want to do the right analysis, you need to select the right model. So that comes with experience only. So when you read more amount of data, more amount of literature, then only you'll get to know, okay, this model can be used for this kind of analysis. And this is the complete data which I have gathered over a period of last 6-7 months in my research. So which model can be used for what kind of data size, what kind of accuracy will be given, interpretability, uncertainty, and best use case. So this is something which I have categorized into this table by collecting a large amount of data set or by reading large amount of data. Again, this is not possible only with me. The team who is working alongside with me are the people who are working with me. So we all have collected this data and we have been working on this particular thing. So that's with respect to choosing the right model for UHPC problems. And then hyperparameter tuning strategies. Again, that comes with selection of the model. So when you select and operate a particular model, that combines with hyperparameter tuning. So when you combine multiple tuning strategies, that gives cross-validation. That is what I was mentioning some time back, K-fold validation. So you can use 10 folds, 5 folds, 15 folds validation. So when we do combination of these models, that will give better output, or that will give better results also, which will also enhance your research at a broader level as well. And coming to the evaluation metrics, which is the last one, that is in evaluation metrics, we majorly focus on coefficient of variation, RMSE, MAE, and MAP. So these are the most commonly preferred evaluation metrics for different models. So whenever you select multiple models in the ML research, try to find all these evaluation metrics for each and every model that you are doing. So that gives you broader perspective about which model is performing at what evaluation metric. That's again something which is good. So mostly we'll report the data with respect to R square than RMSE, MAE, or MAPE, because when you have R square value close to 1, obviously it is impossible to get 1. So the typical range will be 0 to 1. It is impossible to get 1. But if you are reporting the R square coefficient as 1, okay, but that tells that the research is not valid, because no data will give you 100% of results. So typically your values, your R square values can be somewhere around in and around 0.9 or 0.85, that range. Even 0.95 or anything greater than 0.95 of R square value is not typically considered, because you might have overseen the data, or you might have overfitting or underfitting, which is again not a standard way of reporting the data. So keep that in mind when you are going with evaluation metrics also. And coming to the model strategies, there are different models that are available and the different strategies that are available. So this is one of the most famous model, that is K-fold validation model. And apart from that, there are different models that are there. I know I'm talking too much about machine learning, but this presentation overview is all about to give a fundamental perspective about what are the different models that are there. So once you know all these models, it will be easy for you to select or to pick a right model for the right testing standard. So that's the whole point of my presentation here. So, and the common pitfalls where we generally overlook in the data is the data leakage, which is one of the most common pitfall. So we'll collect huge amount of data, but when we test the data, we'll get more amount of leakages. Let's say some data will have some material, some data will have some other materials. So there will be a gap that will be available. So because of that data leakage, again, the underfitting, overfitting, or the performance of the model will get affected. So that's again one common pitfall that we generally see in respect to UHPC or any type of ML-based techniques. And the smaller database, that's again one more thing. So with the database value is less than 100, so that's again gives overfitting, which will not give the better results. So when you have the data set less than 100, so prefer to go with either GPR, that is Gaussian process regressor, or SVR, support vector regression, or any regularized models. Again, when we report any data with respect to less than 100 or 200 or something like that, so the scope of looking into the perspective or reproducibility will become very minimal. So if you give me the same data and if I perform the same analysis, I might not get the same results as you are getting, or I might not get equivalent results or near to your results I'm getting. So that's not possible technically. So try to go with large data set that gives better reproducibility. If someone wants to try out with your data, yes, they can attain the equivalent reports or equivalent values, whatever you have also attained. So don't mix the databases blindly. So generally what we do is we collect multiple databases, multiple data sets without actually looking into what is the data about. So it is also important to know what data you are being used or how you are using, for what purpose you are using. That's the whole point of using machine learning. So keep that also in mind. So these are some of the common pitfalls in ML. And coming to the tools and libraries, so there are different tools that are available. So most important tool is Python. So that's something where we code it, we run it, and we visualize and analyze it. So there are different Python machine learning libraries that are available. One is scikit-learn, which I commonly use, and XGBoost, TensorFlow, PyTorch, Sharp models. These are some of the common models which I have been using. There might be other Python libraries also that might be useful or that might be available. So obviously they are available, but whatever that I have been working in the past 4 or 5 years of my research or past 4 or 5 years of my career. So I'll be looking, I have mostly worked on these basic libraries. Okay. And the data science part, we can use data science and visualization by using pandas, numpy, and all these things. So again, you don't need to learn all of these things. We have different AI tools that are available, such as Claude or even ChatGPT or DeepSeek. You can take the help of these models if you want to fundamentally understand which library is used for which thing and all that part. So if you are also not good at coding, maybe you can take the help of your seniors or your colleagues or your like whoever it is, like your advisor or co-advisor, whoever it is. So maybe you can seek and help from them, and then you can try and sit out together and work out on this. So these are different tools, libraries, and frameworks that are available. So you can have a look into these things when you are working on ML techniques. And the last thing, which is the future research directions and the emerging trends in the UHPC or in general, the machine learning techniques of concrete. So which is federated learning or physics-informed neural networks, which is actually currently gaining the huge market in the huge demand in the market. Physics-informed models are something which are something at a large scale testing we need, but again, it's very good. Even I don't have a large scale idea on even physics-informed neural networks. I am currently working on one of the works on physics-informed neural networks where I'm working on using cementitious waste materials. So when you have cementitious waste materials, how can we use cementitious waste materials in the zone of physics-informed models? Again, I'm at a very beginner level, so probably I need to look into that model also. So this is something which I have recently come across. And there are other directions also, and particularly with the digital twin technologies. Let's say you have a real scale, a real structure, and then you collect the data using sensors. Okay, let's say structural health monitoring perspective, and then you do the modeling. Let's say you can do the modeling in Abacus, or you can do the modeling in, let's say, any other architectural tools that are there in the market. And then you can do the digital twin analysis. Let's say whatever the data that you have collected from the real structure, is it the same data that you are representing from the model which you have modeled in the softwares? That's again one more thing which one of my colleague is working on. So they are working on the bridge girders, particularly with respect to UHPC things. Okay, this is also something which is gaining prominence, digital twin technologies. And the mixed design aspect, that, as I said earlier, so very limited amount of data is there here, and very limited amount of research is also available. So for that reason, if you can focus on structural mixed design perspective, that also gives a wide range of scope, or you can also contribute to the existing researcher or upcoming researchers who are working in the machine learning domain of concrete. So the key references which I have used for preparing this presentation or during my research, which I have used, that there are different journals, different reports that I have studied, and different databases that I have looked. So these are some of the two databases which are more popular for especially the concrete related databases. Maybe you can look into these two databases, or there are other databases that are also available. So maybe you can look into all of these things, and you can look into these aspects also. So these are some of the key references which I have used for my study. And if you want to further read it, so you can go through these things as a primary thing. So the database part as a primary thing, books and reports, these can be used to fundamentally understand with respect to fiber reinforced concrete or with respect to UHPC fiber reinforced concretes. Okay, so these are key references. And if you have any questions, you can keep your questions now, and I'll be happy to answer your questions at whatever level that I am aware of. And I hope this particular session was useful to understand what is UHPC, why do we need UHPC, and at what level we can use UHPC and incorporate ML in the concrete design, particularly in the UHPC concrete design. Thank you all. Thank you once again for giving me this opportunity. Thank you once again.
Thank you, sir. So, Rishikesh sir, you can
Yes.
start question answer round.
Okay, sir. I actually have two questions.
Yes,
First
sir.
is whether we can add the waste plastics, right, into the cement mix that you achieve, right? So to increase the sustainability part, is
Yes.
there any possibility that we can incorporate the waste plastic?
Yes, sir. There
Right.
are actually
Yes.
studies. Yeah, there are actually studies which are happening on waste utilization, which are also published. Literature is also available. So we can use microplastics, or we can use the rubber, the tire rubber. The research is happening on these areas as well. Yes, we can incorporate plastic waste, or even if the rubber waste also we can incorporate in the mixed design. Or even one of my friends who was working on the utilization of chips, the motherboards, RAMs, these things he is utilizing, and he is working on utilization of them in the concrete. So there's a scope of that.
Okay, so my second question was the CO2 produced, right? The per kg of cement,
Okay.
the CO2 emission. So I think that must be very high as compared to the normal cement, right? Because we are utilizing very high amount of CO2. The cement. We are using very high amount of cement. So
Correct.
CO2 emission will be very high per kg.
Correct.
Right. So is there any way to address that issue?
Yeah. Yes, that is where we got, we can use the supplementary cementitious materials, particularly slag can be used, where we can minimize the carbon footprints, or where we can minimize the carbon dioxide thing into the global needs. So we can use some alternative materials, particularly slag can be used as an alternative material. That can also be possible.
Okay, sir. If the audience member have any questions, they can ask in the chat box. I don't think anyone has any
Okay.
questions.
Yes. So we can conclude the session, but before that, on behalf of Doctoral Studies and Research, Dean Dr. Purvi Madam and Associate Dean myself, Dr. Bijal Javeri, along with my team members and Ashwin sir, we are very grateful to your session, which has included so many dimensions, that right data for right model, then certain pitfalls in UHPC research, and so many technical dimensions that you have shared with our scholars. If possible, sir, you can share your PPT. Otherwise, you can share the details that where they can search out certain information, because at the end, in the last slides also, you might have shared so many dimensions of various softwares which can be used for the research. So it would be a really wonderful session for our research scholars. Thank you so much, sir, once again. And we would like to make a great such type of association for research scholar, as you have started your postdoc journey. So we'll get your expertise in that area as well. Thank you so much once again.
Thank you. Thank you all. Thank you once again. Yeah, definitely. I'll share the PPT and I'll share any documentation that is essential for anyone that is in need
Okay.
of.
Okay, fine. Thank you so much, sir. Thank
Yeah,
you,
thank you.
Rishikesh, sir, for arranging the entire webinar sessions along with question answer round. Thank you.
Okay, madam. Thank you.